Okay. Good afternoon, everyone. If you can hear me clearly, please type 1. Alvaro, thank you. Lucas, question. Diego, Muniro. Okay, thank you very much. I just stop the video and quickly explain the things that we need to cover for today. Just can you please confirm that you can see the caption? If you can see the caption, please type 2. And do you have control to disable it if you don't want to see the captions? If yes, okay, awesome. Thank you very much. So you remember we started this chapter 4, aiming to talk about overfitting and getting to 7-step workflow. And we started saying that we have different forms of machine learning, and supervised learning is just tip of the iceberg. We talked about supervised learning, which we have labels to supervise us. We have unsupervised learning that we try to classify to different groups. We want to categorize the output to different categories that we are not sure what label could be suffice or appropriate for them. So clustering and dimensional reduction are the two major subsidiaries of unsupervised learning. And we said that self-supervised learning, because the system provides the label by itself without any human intervention, deserve to have a separate categories in machine learning. And we talked about reinforcement learning right after that. And also we said, right now we have a combination of neural networks and reinforcement learning, which is not mentioned in the book. And that is deep reinforcement learning, which is one of the hot topics that people work on in academia as well as industry nowadays. After that, we started talking about this part, evaluation machine learning models. And we said that in the examples that we had before in the previous chapter, which were the first one was IMDb dataset, binary classification. And after that, we had Reuters multi-class classification and regression. We divided our data into 3 phases. One of them was the training, which is responsible to provide model for us, and validation to dynamically check the performance that we have and how good our model works with actually unseen data. And after all the iterations, we go to a real battlefield, which is testing data. And test data is nothing but never before seen data. We said that, okay, what is the reason that we need to check in every iteration the performance that we have? We can simply just divide the data into 2 parts, and those 2 parts could be just training and testing. But we said that the problem is we do not have any dynamic control. So to have dynamic control, we need to have another portion, which is validation data, which tries to modify the hyperparameters. And if you remember, the hyperparameters are the parameters that we are responsible to manage and modify, like the number of layers that we have, the number of neurons in each layer, and the batch size, and so on and so forth. Anything that we can manage are among the hyperparameters, and the things like weights and biases, that the system is responsible to adjust would be parameters. If everything is clear so far, would you please type 5? Thank you very much, Lucas, Parsa. We get to the next part saying that if you change the parameters too much to adjust the loss function, loss values and accuracy based on the validation data, means that you see, okay, the accuracy is not that much great, so I'm gonna manipulate the number of layers and the number of neurons in each layer to increase the validation accuracy and decrease the validation loss. If you do it too much, it's gonna be kind of indirect fetching the data from the validation data set, which we call it information leaks. And it says that every time you tune the hyperparameters of the model based on the model's performance on the validation set, some information about the validation leaks into the model. We try to avoid that. So, we had 3 different folds of putting aside the validation data set. One of them is simple holdout validation, and that happens when the number of samples are quite large. So we are gonna just, for instance, consider 60% for training, 20% for validation, and 20% for testing. We use that when we have good number of samples. But if we don't have that, what should we do? We should consider something that we call it k-fold validation, 10-fold, 4-fold, or something like that. In this example, it is 3-fold validation. We pick 1/3 of the data set in this example out, and we train our model based on the other 2/3. And we calculate the score for validation of the first 1/3 of the data. But remember, when we go to the next attempt, it's like brand new model. So we don't bring anything from the previous model. This is like we create a model from the scratch. In this one, the second 1/3 of the data would be hold out, and we train based on the first and the last 1/3 of the data. We do the same thing for the last. After finishing all these iterations, we are going to consider the average of all validations, and that average would be the result of this. But it's not going to be always the best, especially when we have very much limited number of samples and we need high accuracy. In that case, imagine that this is one black box, the whole thing. Let's call it black box X. So what if we do whole process once and we get one final answer for it? Then we shuffle the data and we do this for the second time. So if it is X, we are going to have X1, X2, X3, X4, all the way to X10. Imagine that we want to do it 10 times. Then the result would be something like this. Look at this part. Note that you end up training and evaluating 10 3 models. You know what I'm saying? So 10 times those 3 models, which P is the number of iterations you use, and which can be very expensive. We do that only the time that you need high accuracy, as well as the time that you have limited number of samples. We said that the data representation should be the way that any portion of the data that you pick should be representative of the whole data set. So if it is already sorted like iris data set that you worked in assignment number 2, if I'm not mistaken, or assignment number 1, not sure. Anyway, so you need to shuffle it before you start working on it. Otherwise, if you, for instance, get the first 2/3 as the value as the training and the last third as the validation, it would be horrible because you don't have any sense of Virginica in your training and you want to test it based on the things that you have never trained. The question is, should we always shuffle the data set? The answer is no. When you have a trace of time, or you have kind of a sequence that X is happened after X minus 1 and would be before X plus 1. In that case, if you shuffle the data, you can't find what is going to happen next because it has a trace of time, right? In the stock market, weather forecasting and these kind of things that you want to predict future based on the history, you cannot shuffle the data. And we said that the worst thing that we can do is having redundant data, and we test or validate the data based on some records that you have already trained your data set, your model based on that. Sorry. By saying that, we quickly reviewed everything, guys. If Matthew asked that, so if the data has a sequence that is important to track, shuffling would invalidate the data, and that is absolutely correct, right? Matthew, imagine that we have the data for the last 100 days for the stock market, for example, right? We always pick the first portion as the training part. Imagine that in the simplest scenario, we want just to have training and testing, right? So we take the first 80%, for example, as the training part, and we test the last 20 days because it's pretty close to the current day, and it helps us to predict what is going to happen in the future, right? Give me a second, please, because that's a very valid question. I want to spend a few seconds more on it. Okay. So imagine that I just want to see the stock market for something like RBC, right? And imagine that we have 80% for training and we want to predict what is going to happen. We want to test our system. The logical way is to train based on this part, the first part, and test it based on the last part. Because technically we want to see what's going to happen next, right? If we test based on the first portion, it's not going to give us very brilliant result. Does that make sense? Matthew said that could we split the data into sets and shuffle the sets to increase the accuracy? It's not going to help us to increase the accuracy. It's going to imagine that here, this one after shuffling would come, for instance, here, and this minimum value, it's going to get to the last, for example. So we can't understand what is happening, what is the trend. Shuffling is something that's not going to help us. It's going to actually exacerbate the accuracy, not increase the accuracy. Because the mark foot of time is one of the parameters that we see. The data today is impacted by the data in the previous day, right? Does that make sense? Okay. Thank you very much. Lucas said it makes sense. Time series data is let me just share that with everybody. Lucas said it makes sense time series data is very dependent on how the data before behaved, like time minus one. So shuffling would break this chain and invalidate the data. Thank you very much. So people who watch the recorded session, you can just see what our friends talked, and I tried to answer them. Okay, so if you don't mind, let's go to the newer parts that we want to discuss for today, and that is data preprocessing, feature engineering, and feature learning. So the major question is, how do you prepare the input data and targets before feeding them into a neural network? One quick question. For something like the first example, MLIS, did we do any feature engineering? Did we do any change pre-processing in the data? Do you remember anything by any chance? This is just for the reading. You remember that the output that we had, they were like 0, 1, 2. Yeah, awesome. We did some changes, like what? The numbers were between, and now I'm capable of explaining further and deeper why we do so. Imagine that we, my apologies, just give me a second. So imagine that we keep the pixels values in the range of 0 to 255. The problem is when the values are in a large scale, it is going to be very hard to calculate the loss, and relatively, it is going to impact the optimizer to calculate and appropriate derivatives and change the gradient that can converge the weights and biases towards getting the optimal result. Does that make sense? If the range is between 0 to 1, it is easier for the loss function to calculate and bring back the result to optimizer and adjust the next step, right? It's going to be easier for that. So that is why we normalize. And as Lucas was kind to share, we did that by dividing by 255. Is easier to work with this one. And why easier? Because the weights and biases should not go crazy by any changes that happens. They are just be converged into a small portion and small. The question is it possible to do and proceed without doing that normalization? The answer is yes, but with the cost that you impose on the system to take further steps to converge. Does that make sense? Guys, if you don't mind, I'm going to keep sharing the questions. This is gonna be easier. And if there is any private message, I'm gonna ask people to type 1 or something to hold it, to bring it up, not to be clear. So derivatives for low power is easier than the higher exponents. That's exactly what the book mentioned, and Lucas even paraphrased that in a nicer way. Thank you, Lucas. I do appreciate it. So let's, by what Lucas said and what we described now, let's go further. But beforehand, I want to first think, I want to apologize for changing tomorrow's delivery system into online. I talked to Maziar and I said, I'm not sure how I will be in tomorrow's morning. So what do you think? Should I wait? And give kind of final moments notice if I cannot come, or it's the best to decide it now. And we come up with this idea that let's not take any risk. So hopefully, I hope that I can just, at least with the same way that I deliver today the content, tomorrow we will have online session. So I have announced it on the group, Telegram group. I announced it on the Desire to Learn environment, the course webpage. And my apologies for having a typo. First I said Thursday, which we never have any lab on Thursday. And that was a kind of indirect of proving that I don't feel very well. So it's gonna be tomorrow. I have shared all the links. So feel free to join any section that works the best for you. And please, if you are in touch with any of your other friends, although I have announced, please just tell them again. I don't want anyone to come from long distance and then realize that the class would be online. And thank you very much for collaboration and understanding. Is there any concern, any question about tomorrow's session? If everything is clear, please type 5. Thank you, Parcel, Lucas, Agor, Eric, Eli. Okay. As one of the things for tomorrow's presentation, because I'm not able to take care of the attendance, people might come to a portion of the class and might leave, for instance, 5 minutes before, and I don't have any way to control that, okay, who is in the class, and I might lose some of the friends' attendance. I decided to give the present mark, the lab mark, to everybody. So if you see that there is one already in your lab number 9, that is the reason. And for lab number 11, I have already given the presents to everybody, and the reason for that is we are getting closer to the end of the semester, and people might use their time wisely, and they want to just dedicate that time to the term project or anything. Although I would be more than happy to see you in the labs. That's your choice to just watch the recorded session or come to the class. Oh yeah, thanks for asking. Yeah. And let me ease the job. Oh no. Yeah, there we go. Okay, today's at class is this one. And tomorrow's at class for the sections would be this, just to ease the job. Any other question, any concern? Okay, if not, let's just keep going. My pleasure. The thing is, well, many data pre-processing and feature engineering techniques are domain specific. So the data pre-processing for neural networks are classified into 4 different categories. I'm not sure how far we could get, but the questions that I have designed for the MCQ belongs to 4.3. So the safest is to wait till tomorrow night, and then start, working on the quiz. Then you should be sure that we have covered everything, unless that you want to read the content and then start the quiz. So we have 4 different ways for pre-processing, and we have already worked on some of them. One of them is vectorization, normalization, handling missing values, and feature extraction. So let's see one by one what is happening in vectorization. Anything that our deep neural network want to deal with is based on a kind of vector. So that's why we call it vectorization. We need to convert it to a kind of vector, right? All inputs and targets in a neural net must be tensor of floating point. In rare cases, we could accept integers for input or for output. You remember, instead of having hot encoded form of digits from 0 to 9, we could use integer outputs, right? So that is why it says that in specific cases, we could accept integers as well. And in assignment number 2, we could use either of them. For setosa, we could use 1, or we could use 1, 0, 0. For versicolor, we could use 2, or we could use, I'm fabricating numbers, it could be 0, 1, 2, it could be 1, 2, 3. We could use 2, or we could use 0, 1, 0, the same for Virginica. So you must first turn them into tensors. That is what we call it, data vectorization. In the 2 previous text classification examples, you remember that we had a kind of series of numbers. You remember we had 1, 17, for example, 22, 1073, something like that. So we had those list of integers starting for frequencies of words, standing for frequencies of words. And we used one hot encoding. Actually, first we tried our own function that we have written ourselves, and then we used the predefined library functions that we had in Python to turn them into a tensor of float 32 data. That is what we call it, actually, vectorization, converting anything to vectors of data. And value normalization, as Lucas was kind to share, is simply lowering down the range into something between 0 to 1. Actually, this is one of the MCQ questions, but I changed them later, so now I feel comfortable to share it with you. It was like this: which one is the value normalization in general? So each feature independently should be normalized so that it had a standard deviation of 1 and the mean of 0. So I said, for instance, standard deviation of 0 and the mean of 1, 1 and 1, 0 and 0, something like that. So now you know we take the mean out of every single cell. In that case, it's going to change the mean from whatever it is into 0. So the mean of the whole column would be 0. And then we divide it by the standard deviation. So it brings the range into something that the average is equal to 0. And the standard deviation would be 1. In general, it is safe to fit into a neural network data that takes relatively large values or data is heterogeneous. Then you're going to just apply that to normalize it, to make learning easier for your network. Your data should have the following characteristics. First, typically, most values should be in the range of 0 to 1. Why it says that most of them? Because if you see, we have some values that are a little bit more, a little bit less, but they are centered into 0, and the standard deviation is just 1. Be homogeneous, so you don't need to worry about that. The crime rate is, for instance, between 0 to 10. The square feet of the house is between 400 to several thousands, right? You bring them all into a range that are amenable for the system, for the model to deal with. So now let's just see, normalize each feature independently to have a mean of 0. It happens here by taking out the average from every single value of the column, and then divide them by the standard deviation. So normalize each feature independently to have a standard deviation of 1. This is what we did in a few algorithms that we have gone through in previous sessions. If you are curious about this, I explained it in the previous lab and a week before the midterm, before the reading week. So I explained this extensively too much. Now let me ask you one question if you're willing to participate. If we do that on the training data set, should I calculate the average of the test and calculate the average of the test and take it out of the test? Yes or no? If you think that I have to calculate the average for the test separately and then take it out, please type 1. If you think that I have to use the average of the training and take it from the test, please type 2. So what do you think would be the best? Okay, I ask the question again. Imagine that you want to take the average out from the training as well as testing data set. Should we calculate the average for the training set and take that from training set and calculate the average for the testing and take it out from the testing separately? Or should we just calculate the average? That was option 1. Option 2 is calculate the average for the training and take it out from training and testing. This is option 2. Which one do you think makes more sense? 1 or 2? So one of the friends said separately, which is option 1. One of the friends said option 2. Right? Anybody else wants to participate? Okay, look at this one. Here we calculate the mean once based on the training, right? And we take the mean that is based on the training data set out of the training data set, and we use the same number, the same mean, and take it from the test data set. And if you ask why, that is the reason. It says that note that the quantities used for normalizing the test data are computed using the training data. But you may ask why. You should never use in your workflow any quantity computed on the test data, even for something as simple as data normalization. So is it clear now? So that is option 2. We use mean based on the training, and we take it from both training and test data set. If it is clear, please type 1. Yalor, Eric. Meanwhile that I get to, and meanwhile that I get to the page, would you please check the quiz and see if it is visible now? If it is visible, please type 5. Okay, thank you. So So we talked about the normalization, and now we have better understanding. And the third pillar of feature engineering is handling missing values. I have a quick question for you guys. Imagine that in a numerical column, we have a missing value. What is the best approach for that? If you have a missing value, what is the best approach for that? We talked briefly about it before. Matthew said remove it. Absolutely correct, Matthew. When the number of records that we have as the sample, for instance, you have 1 million records, and 1,000 of them they have missing values. So we take no risk, and then we drop those values, right? But let's go to yeah, actually, Matthew, you said all the correct answers even before asking. Awesome. How about I wanted to ask this question: that how about the time that we don't have enough samples? So removing those samples significantly will impact negatively on the accuracy of our model, right? So one of the approaches that we could have, as Matthew was kind of, let me just share the answers. So the credit goes to Matthew for saying that we can make them 0, for those values, right? It is totally fine. We convert them into zeros, right, for those missing values. But there is just one exception kind of scenario. What if 0 has a kind of meaningful value in our data set? In that case, we shouldn't use zeros. Does that make sense, Matthew? So the first things that you said, remove it when we have lots of data, that is perfectly fine. The second one, that we convert them to zeros, because after a while, system would understand that, we have zeros here, you know what? So zeros means something is not correct. We have missing values. Technically, system is gonna just treat them as missing values. But what if we are talking about something that 0 has a kind of specific meaning? In that case, the 0 would not be as safe. We could just reserve another number like minus 999, something like that, or 999 when we don't have any specific meaning for that. We are gonna have a kind of convention. We reserve a number that has no meaning for just missing values. That is one of the things. But we have another problem I'm going to talk about. Let's just quickly see those things. In general, with neural networks, it is safe to input missing values as zeros with the condition that 0 isn't already a meaningful value. Note that if you're expecting missing values in the test data, in this paragraph, let me just summarize it. They want to say that what if your training data is nice and neat, no missing values, right? But what if I prefer to have participants like Matthew to guess, because I can learn even more by sharing your opinions instead of just saying it by myself. So what if we have missing values in our test data set, but we don't have any missing values in our trained data set? What is the best strategy to solve the problems, to create models? Do you have any opinion? Yeah, imagine that, Matthew, we have no missing values in our trained data set, but we might have missing values in our test data set. So technically, we should have issues when we deal with test data set, right? We do not have any exposure to missing values in our model because it was trained based on the flawless data set, no missing values. So what should we do? Prakash, it is possible, but the whole idea is to have, listen to this part, Prakash. We want to have answer for test data set, right? That is why we call it test data set. Deleting any rows from test data set is like wiping off the problem statement. You know what I'm saying? People expect us to bring labels for them, not to delete, omit them. Okay, let me tell you the most logical way. Guys, we are gonna replicate, we are gonna copy and paste some records in our training data set several times. And we randomly, artificially make some missing values in them. Does that make sense? We make some artificial missing values. We just change them. We copy and paste a few and make missing values intentionally to mimic the test data set. Does that make sense? Did you get this, guys? Everybody? Okay, awesome. Thank you, Anand, for confirmation. Let me just quickly see that. Note that if you're expecting missing values in the test data set, but the network was trained on data without any missing values, the network won't have learned to ignore missing values. In this situation, you should artificially generate training samples with missing entries. Copy some training samples several times and drop some of the features that you expect are likely to be missing in the test data. In test data. Okay. By saying that, we get to the last portion that I want to talk and discuss and finish for today, and that is feature engineering. Okay, imagine that. Guys, I'm gonna first tell you the whole scenario, and let's just use this one. My apologies. Let me just, okay. Not to distract you, imagine that that is the problem statement that we have. Sorry. That is the problem statement that we have, and that is having photos of old-fashioned form of clocks. We have kind of short handle, long handle, so for the hour and for the minutes. What could be, to the interest of time, I can't unfortunately ask you to guess. Let me tell you, one of the things that we can do is to write lots of lines of code and then calculate the pixels of the long and short handles, right, in different columns. And then having, we need to have quite extensive number of samples to guess what could be the hour, right? A little better could be, okay, just first get rid of these unnecessary information that we have cloning our data set from those minutes and hours things here, and then we calculate the coordination of the clock hands as you see for the long and short. And after that, we are gonna do what? We prone our data, we do some feature engineering, and then, but what could be the best approach for it? Before anything, let me just quickly read that for you. Guys, feature engineering happens based on the knowledge that you have on the data. You know how to read the the old-fashioned form of clock and people how to just read them. So you're gonna try to mimic that in your algorithm, right? So feature engineering is the process of using your own knowledge about the data and about the machine learning algorithm at hand to make the algorithm work better by applying hard-coded, non-learned transformations to the data before it goes into the model. So if you just bring the raw data that you have, it's not going to go that far. And it's going to be very much complicated for the neural nets or any algorithm. Sometimes it is impossible without doing feature engineering. So it says that the data needs to be presented to the model in a way that will make the model stroke easier. Guys, please tell me if you have a chance to find a solution based on hard-coded, just some lines of algorithms instead of using deep learning, which one do you prefer, to use deep learning or traditional coding? This is the last page, by the way. Exactly. Look at this explanation. It says that if you choose to use the raw pixel of the image as input data, then you have a difficult machine learning problem. You'll need a convolutional neural network to solve it, and you'll have to expend quite a bit of computational resources to train. A little better thing is, but if you already understand the problem at a high level because you know how to read the type, then you can come up with much better input features. And for instance, it is easy to write a 5-line of code to just pick the coordinates of each hand, right? And then it says that, what if we just define something even better, like your features are making the problem so easy that no machine learning is required. By changing the problem into this, you calculate the angle of this and the angle of that, and simply you just need to use one rounding thing, right? Round this to the closest, which is 3 for this, for example, right? And round this, which is going to be 10 in this example, and so on. So you just need to use traditional. It says that you can go even further, do a coordinate change, and express the x and y coordinate as polar coordination with regard to the center of the image. Your input will become the angle theta of each clock hand. At this point, your features are making the problem so easy that no machine learning is required. That is the ideal form. I said ideal is no machine learning, no deep learning, just a simple programming. A simple rounding operation and dictionary lookup are enough to recover the approximate time of day. And it says that classical shallow learning didn't have hypothesis space rich enough to learn useful features by themselves. If somebody asks you that feature engineering are needed for shallow learning, the answer is 100% yes. Is it mandatory for deep learning? The answer is no. But is it useful? We are gonna answer that by reading the last. My apologies to keep you waiting for 2 more minutes compared to the standard. Lucas said that sometimes DL might overcomplicate the representation and might overlook the simple convention that is not aware of. That's absolutely right. Thank you, Lucas. So it says that fortunately, modern deep learning removes the need for most of feature engineering because neural networks are capable of automatically extracting useful features from raw data. But the question is, does it mean you don't have to worry about feature engineering? No, and there are 2 reasons. First, good features still allow you to solve problems more elegantly while using fewer resources, especially when you have limited number of rows and samples. Feature engineering can help you a lot, and good features let you solve a problem with far less data. If you have only a few samples, then the information value in their features become critical. Guys, thank you very much. Tomorrow, we are going to start from page 104 and try our best to finish chapter 4. And I'm going to close the, for those who want to submit, if they haven't done it yet, I'm going to close the submission folder by tonight, and I'm going to open submission folder for assignment number 3. And that's pretty much it for today. Thank you very much. And my apologies if the sound is not as normal. Have a wonderful one. If there's any last minute question, please let me know. Otherwise, have a wonderful rest of your day. Take care. See you online tomorrow. Thank you, Matthew. Thank you, Ivan Parsa. Thank you. Have a good one. Bon